Hi everyone, and welcome to this presentation within the 5th Robot Learning Workshop at NeurIPS 2022. I'm Luca Carlone, I'm an associate professor at MIT, and today I'm going to share this presentation with Rajat Talak, who is a research scientist in my group. Today we want to share our vision for certifiable perception and describe work we have done on certifiable outlier-robust estimation and more recent work on self-supervised learning. So the topic of this presentation is spatial perception. What is spatial perception, really? Imagine that you have a self-driving car navigating an intersection. In order to navigate safely, the self-driving car will have to detect the boundaries of the traversable space, detect other cars and pedestrians, track the speed of other cars, detect traffic signs and traffic lights. These are all spatial perception problems. In other words, I'm going to use the word spatial perception as a broad umbrella for challenges ranging from localization and mapping, object detection and pose estimation, object tracking, semantic understanding, and more. So one of the key observations behind our work is that perception is a key ingredient in safety-critical applications of autonomous systems. And indeed, failures of perception algorithms and systems can induce catastrophic system-level failures. For instance, here I have an example that goes back to 2018 of a Uber vehicle where the perception system failed to detect a pedestrian, resulting in the killing of a woman in Arizona. And unfortunately, there are several other examples. On the right, I have an example from Tesla. The autopilot failed to detect the concrete obstacles on the left of the car and decided to turn into it, killing the passenger. And at the bottom right here, I have popular examples in which simple markers and stickers can lead a neural network to misclassify a stop sign for another traffic sign. Not only here, but these examples are back to a few years ago. Unfortunately, things are not really getting better. There is a recent article from Business Insider discussing the state of self-driving. In the article, essentially, it is described how the number of deployed vehicles is quickly increasing over the years. For example, the number of cars deployed by Waymo increased by a factor of 3 between 2020 and 2021. But unfortunately, so are increasing the number of collisions and accidents. And in particular, in this slide, I have the number of collisions comparing 2020 and 2021, where on the left table, the number of collisions are classified by the type of collisions, while on the right-hand side, they are classified by the car manufacturer. And for example, you can see that Waymo, while increasing by a factor of 3 the number of vehicles, is also observing a 3 times or more increase in the number of collisions. Of course, perception is not only crucial to self-driving, but is really crucial to any other safety-critical application of robotics and autonomous systems. At the top left, I have an example of search and rescue with drones, for example. Of course, here, correct perception can make the difference between finding survivors or failing to do so, so you can understand how important perception is. Perception is crucial for human-robot collaboration. If the robot is failing to understand the intention of the human or the external environment, can just pose a danger to the human himself, in this case. Domestic robotics, in some cases, can be safety critical if you have large robots that have to operate in complex environments, such as the kitchen. And of course, moving to very different application of robotics. In the case of space robotics, failure of perception can also cascade to catastrophic failures. For example, in debris removal applications, if the spacecraft is failing to understand the shape of the object to pick up and remove, this can also lead to catastrophic failures. So over the last few years, we've been focusing on this idea of certifiable perception, and really, even before going to discuss about algorithms, we've been motivated by 2 main research questions. The main research questions are the ones that I'm stating in this slide. The first question is, can we develop methodologies to ensure that a perception algorithm or system is behaving as expected or detect failures otherwise? We want to guarantee that an algorithm is either producing the right answer or is detecting that it's not able to do so. And the second question, which is related, is can we understand under which conditions a perception algorithm is expected to perform well? Can we understand for which set of inputs an algorithm is expected to give the right outputs? And we believe these are very relevant questions because once you're able to perform, for example, fault detection, you can immediately apply mitigation strategies to avoid that faults in perception system are cascading into system-level failures. In case of an accident, you can use these techniques to trace back the cause of the failure, in case there is an investigation, for example. And as we're going to see in the second part of this presentation, once you're able to detect and to distinguish correct results from incorrect results, you can also use the correct results as a source of training data for self-supervision. The second question is also very relevant. In a sense, we are asking what is the set of inputs for which the perception system is supposed to work? Well, in self-driving cars, this is what is called the operational design domain. So answering this question can help answering a more general question about where it is safe to deploy a self-driving car, where is it safe to deploy a robot, for example. And of course, if you can characterize the set of inputs for which our algorithm is performing as we want, we can also inform the process producing this input data with the corresponding constraints. And in general, we're interested just in understanding the fundamental limits. What is the best performance and what are the limitations of the algorithms for perception we are developing? So in order to answer to these questions, today I'm going to mostly focus on the first one. We've been doing a lot of work over the last few years with my group. And today I'm going to summarize some of the work. I'm going to start covering the idea of certifiable perception algorithms for estimation, and in particular for object pose and shape estimation. This is more traditional work about outlier-robust estimation. Then I will pass it to Rajat, who is going to cover more recent work about certifiable learning models and connections within the idea of certification and self-supervised learning. And then I wanted to mention at the end, we're not going to have time to cover that in the presentation, but very relevant work from my group connected to the topic of this workshop on Trustworthy Robotics is the work on monitoring of perception systems. Again, I do not have time to cover that during this presentation, but if you're interested in runtime monitoring, go and check out the papers from the first author, Pasquale Antonante, both published at titles last year, as well as the more recent work on arXiv this year. So let me start talking about certifiable perception algorithm for object pose and shape estimation. I'm going to start with a running example about 3D object pose estimation just to make the discussion grounded. So imagine that I give you an image. The goal here is to estimate the pose of the object in the image. In this case, of course, is a car. What we're going to do is to take a feature-based or key point-based approach to object pose estimation, which works in 2 steps. The first step is detecting features or key points from the image. So here, typically, we use a neural network, which is detecting points of interest in the image. And these points correspond to specific points on the car. For example, you are detecting the wheels. The network is trained to detect the wheels, the headlights, the corners of the windshield, which are corresponding to specific points on the car. And then step 2 is to use these key points or these features to perform estimation, where, for example, given a CAD model, we are trying to fit the CAD model to these key point detections in a way that the CAD model is projecting at the right location in the image. For example, here, on the right-hand side, you see the silhouette of the projection of the CAD model, and you can see that it's projecting at the right location in the image, so this is a correct result. Unfortunately, things in practice do not go always this smoothly, as in this slide. A more typical setup is the case in which I want to perform, again, object pose estimation for the object in the image. I take a state-of-the-art neural network, and the neural network sometimes will do a good job at detecting features and will produce a number of correct detections. These are what we call the inliers. But at the same time, we'll also produce a number of misdetections or outliers. These are points that are not really corresponding to what we expect. For example, if the neural network is detecting the wheel of the car here or the headlight here, that's definitely an outlier. The issue that we face here is that if the neural network is producing too many outliers, then the estimation block will just fail in the presence of too many outliers and will produce an incorrect result. For example, here the silhouette of the car is the one in yellow, produced by the estimation algorithm, which as humans we realize is not the correct location of the car. So the work we have been doing over the last few years, and I want to cover in this part of the presentation, is how to make the estimation stage, the second stage of this pipeline, as robust as possible to outliers. The second stage is something that is typically called the perception backend. And in particular, the perception backend is typically solving an optimization problem whose solution corresponds to the estimate we are looking for. The optimization problem, for example, can be looking for a variable x. In this case, that's the pose of the car. And it's doing so given measurements yi. These, for example, are the key points detections in the image. And in particular, the minimization is minimizing the residual error r between the x and the yi. You can imagine that the residual error is measuring how well the x is fitting the measurements yi. And in particular, we typically don't just minimize the residual error r, but we also put some robust loss function rho, which again is aims at increasing the robustness to outliers. And if you're able to solve this optimization problem, we can get a good estimate of the pose of the robot in the image. This optimization problem is very challenging to solve. First of all, it's very general. You can find the same optimization problem for other pose and shape estimation problems. For SLAM, you always end up solving some sort of optimization problem, but it's a challenging one to solve. The measurements yi are noisy. We said that many of those are outliers. And also the problem is non-convex, meaning that it's a tough optimization problem to solve. And in some application scenarios can be also high dimensional. For example, if we estimate the pose and shape of the vehicle, the x will end up being a large vector. Some of you might try some standard techniques. For example, for certain problems, RANSAC is a standard algorithm, or can even say, why don't we use gradient descent on this algorithm? Well, the truth is that because of the non-convexity, both Ransack and gradient descent can get stuck in local minima, which are bad solutions. And not only will this get stuck, but will not be able to detect if they got stuck. So they will give an estimate, and they will not be able to understand if the estimate is correct or not. The estimate can be completely wrong. And that's one of the main motivations, one of the main reasons why we really care about developing certifiable algorithms that can instead certify that they got the right solution. In particular, over the last few years, we proposed a set of algorithms and what we call the Certifiable Perception Toolbox. The Certifiable Perception Toolbox is a set of algorithms aiming at solving robust estimation problems in robot perception. In the running example before, I was talking about pose estimation from images, but the truth is that we can solve, in the methodology I'm going to discuss, are going to solve a broad set of perception problems, including object pose and shape estimation from point clouds, or even simultaneous localization and mapping. All these problems are characterized by the fact that they can be phrased as optimization problems, where we figure out some variable x by solving by minimizing a robust loss function. And essentially, the set of algorithms that we developed are aiming at computing a solution to this optimization problem and either certifies optimality or detect failure otherwise. That's the idea of certifiable algorithms. In particular, we've developed a number of methods, including Robin, which is a graph theoretic approach to prune and rule out gross outliers. I'm not going to cover that in today's presentation. There's just a way to filter out some of the measurements which are trivial outliers. Then graduated non-convexity, which is just an optimization technique to make sure that we can more easily convert to global solutions of this optimization problem. I'm going to cover that in the next slide. And then a fairly unique contribution about certification, where we develop semi-definite moment relaxations to either certify that an estimate is globally optimal or to detect essentially that the estimate is incorrect. And I'm going to just provide a slide about this in the following slides. So let me start with GNC, or graduated non-convexity. The goal here is not to go over the technical details, but just to give you the high-level overview of the algorithm. The problem is that we want to minimize a non-convex cost function. It's the same problem I was showing in the previous slide. And remember that if you get to the global solution of this cost function, we can essentially retrieve a good estimate of the object we care about, of the variable we care about. While if we are stuck in some local minimum, that corresponds to a poor estimate of the variable we care about. And this is a non-convex problem, right? So these are all these valleys, and we don't want the algorithm to be stuck in one of these valleys. The idea of GNC is quite simple. If the non-convex problem is hard to optimize, let's start from a convex approximation of the non-convex problem. So that's a convex approximation when there is a single minimizer. Let's minimize this and compute some solution, and use that solution at the next iteration. At the next iteration, we can increase a little bit the amount of non-convexity and use the previous solution as initial guess and optimize again. We can increase again the non-convexity and optimize again. And gradually, we keep increasing the non-convexity until we retrieve the original non-convex cost function that we want to minimize. As a trivial observation here, I'm visualizing this optimization problem and these cost functions as a single line, as a 1D cost function. In practice, these are high-dimensional cost functions, so this is just for the sake of visualization. Indeed, if you like a 2D visualization, this is a visualization of GNC. We want to minimize a non-convex cost function. We start with a convex approximation, and the convex approximation gradually becomes more and more non-convex until it goes back to the original cost function, and we minimize the original cost function. So for those of you who have some, maybe they're from computer vision, you might know that actually GNC is not something that we proposed. GNC is a quite old technique that goes back to early vision problems and to Blake and Zisserman from the book of visual reconstruction from Blake and Zisserman in 1987. What we really do is we rediscover GNC and figured out that it can perform very well in robust estimation problems as the ones showing up, for example, in object pose estimation. So in this slide, GNC is a technique that can essentially converge to better solutions of the optimization problem, but is not guaranteed to converge to a global minimizer of the cost function that we want to minimize. That's why we have to develop some technique to certify optimality of a given estimate. And in this slide, I'm just summarizing the key idea of our approach to certifying optimality. These are kind of new mathematical tools from optimization theory. I'm not asking you to understand all the details from this slide, but I think they're pretty nice and recent tools, and they're quite unexplored in the robotics community. So there are a lot of opportunities there to apply these tools and do even more compared to what we have done so far. So there are a lot of opportunities there. But just to give a sense about the way we certify optimality, essentially we take an optimization problem, which is the robust estimation problem we started from. That's non-convex, it's tough to solve. We show that for a broad class of cost functions and residual errors, this optimization problem can be converted into a polynomial optimization problem. This is nothing scary, it's just an optimization problem where both the objective and the constraints are polynomials with respect to the variable we care about. And once you get to this polynomial optimization problem, first of all, we didn't gain too much because polynomial optimization is still non-convex and hard. What we gained is that for polynomial optimization, there is a very systematic way to compute the convex relaxation of this problem. And in particular, using the tool which is called Lasserre moment relaxation, we can get to a semi-definite programming relaxation of the polynomial optimization problem. So keeping things simple, we can just transform a difficult problem, which is the one we started from, into something that is convex and can be solved in polynomial time. After we do this conversion, we can easily get results such as the informal theorem and here, for which if a given estimate x is optimal for the convex relaxation, then it's also optimal for the original non-convex problem. And we can get, we can therefore check optimality on the convex relaxation. The advantage there is that the optimality of the convex relaxation can be checked in polynomial time. So we really have a polynomial time algorithm that can check if an estimate is optimal. And these indeed are the first polynomial time algorithms that can verify optimality in Outlier-Robust estimation. Of course, disclaimer here, polynomial time does not necessarily mean real time. For example, these algorithms, while GNC and the other algorithms in the Certifiable Perception toolbox are quite fast, the certification part is still running in seconds to minutes, so it's not something that is real time yet, and there is more research to be done to make this into a real time approach. In this final slide of this first part of the presentation, I just want to cover just the impact and result that we can get by applying the algorithms we developed over the last few years. And I'm showing application to different problems, including object pose and shape estimation in 3D point clouds, from camera images, or even simultaneous localization and mapping problems. And from the statistics, we get essentially algorithms which are robust to a large number of outliers, including 95% random outliers in point cloud object detection from point clouds, 70% in object detection from images, 90% in post-graph optimization for simultaneous localization and mapping. Most of these algorithms at this point are released open source. Teaser is one of such algorithms, it's on GitHub. GNC is implemented in GTSM, which is a standard library for estimation for robotics, and is also implemented as part of MATLAB's navigation toolbox. So at this point, I will finish this part and I will pass it to Rajat, who is going to extend this idea of certification and apply it to learning-based models and discuss how that enables self-supervised learning. Rajat, the stage is yours.
Thanks, Luca. Hi, everyone. Before we move to the question of certifying learning models, let us recap the key idea of certifiable algorithm that Luca discussed. A certifiable algorithm mandates that along with producing a solution, we should also provide a binary certificate that can quickly compute if given a solution is correct or not. So in the figure here, for example, we have two algorithms. One produces a red solution, the other produces a blue one. But with the certificate that we have for both the algorithms, both are certifiable. And this is because now with the certificate, we know when an algorithm fails and when it succeeds. So many of the perception backends that we have can be certified this way using the toolbox that Luca described. However, we would like to certify the entire pipeline. That is, we would like to know when the entire pipeline gets something right and when it doesn't. A thing to note here is that increasingly the perception front ends are now learning-based models that use neural networks like convolutional neural network and point transformers, etc. So certifying a pipeline with these models is a slightly harder problem. So the question that we ask now is that can we extend the definition of certification that we saw for optimization solvers to learning-based models or joint architectures that we have in the perception pipelines? So just to think of what we do, so we have some input that comes in from the sensors, and eventually after a lot of processing, we get an output X. So we can think of it more abstractly as an input X coming to a model M that produces an output. Now this model M is trying to solve some problem, call it P, and this problem is instantiated by the input and let's say the set of solutions that given an input X has for this problem P is given by S of X. So given the input X and output produced by the model Z, we say the input-output pair XZ is certifiable if Z lies in the solution space S of X. And a certificate that gives us this, we call it a certificate of correctness. And a model that is able to produce such a certificate along with the output Z, we call it a certifiable model. A model, on the other hand, along with the certificate of correctness, if it also produces a certificate of non-degeneracy, we call it a strongly certifiable model. Now, a non-degeneracy certificate basically ensures that the problem with the given input X has a unique solution. Now, given these definitions of certifiable model and strongly certifiable model, here's a question that arises with respect to learning models as opposed to certifiable algorithms. And that is, once we have these certificates in place, once we say define these certificates for a problem at hand, can we then use them to self-supervise the pipeline? So what the certificate gives you, it tells you whether an input and an output is a correct one for what we want or not. So ideally, we should be able to use that as a signal to supervise our model as well. So what we show in this paper is that it turns out that we can indeed use a certificate such defined to self-supervise. And we sort of show this for object pose estimation from depth point cloud. So for example, we define a certificate of correctness between input X, which is a point cloud, and an output Y, as long as the output Y is able to explain X with some geometric consistency. We also define in this paper a certificate of non-degeneracy, which says that there is a unique pose that can explain the input. Now, that is important in the pose estimation because you can end up with an input point cloud, so that there are more than one ways to fit a CAD model, say, for that point cloud. And the interesting thing that we show is if we use just the certificate of correctness in our self-supervised training, which I'll go through in some time, is that if I just use the certificate of correctness, right, in the self-supervised training, then as the training progresses, the fraction certifiable on the training dataset, which is a dataset that the model would have never seen before, keeps increasing, and it slowly increases mostly to 100% for many of the models that we train it on. So let's do a deep dive and see how this actually works. So object pose estimation. Now, there are multiple ways you can do pose estimation using point clouds. One way to do it is like having some sort of feature detector, local feature descriptors that detects these features or descriptors on the input point cloud, and then in the back end, what you do is do some sort of Outlier-Robust 3D registration. Another way to do it is like directly trying to regress a pose from the point cloud using a neural network. But it turns out that pose estimation does better when you have some knowledge about object semantics. So what we do in our case, we use annotated key points on the CAD models. So unlike the feature descriptors, these are fixed set of key points, and they represent object semantics. So for example, for this chair, we have 4 key points for the 4 legs, 4 more for the seat, and 2 more for the back. So what the semantic key point detector is trained to do is it's trained to detect such key points, but it's trained in simulation. So what happens is when you put it on a real world data which it has never seen before, it fails and it produces errors. So what we do to correct for these errors is add a keypoint corrector. And a keypoint corrector basically solves an optimization problem. It's a declarative layer. It adds a delta to each detected key points and tries to correct for that error by solving this optimization problem that uses the information in the CAD model and the annotated key points so as to correct the key points in the detected. So now what we also do is, like, because we need this block in the training, we show that even though this corrector is a very non-convex optimization problem, it can be implemented with a very simple backprop, and we show this in a theorem in the paper. So now with this correction, what happens is, like, it gives us some advantage in terms of sim to real gap So the models on the real data go from very low certifiability to maybe 20-40% fraction certifiable, but not all the way up to 100%. So what we do then is to use our certifier to self-supervise, and the way we do that is in the training loop at each SGD iteration, we only train on the input-output pairs that are certifiable. That is for let's say after sampling a batch, you compute a loss, but we account for loss only in the certifiable input-output pairs, and we train it with iteration. And the surprising thing that we observe is as the training progresses, the fraction certifiable keeps increasing and increases to almost 100% in many cases. So we did extensive experiments on synthetic dataset generated using ShapeNet, as well as using real RGB D images from YCB using just the depth, of course, and we saw that our self-supervised model is able to match any a supervised baseline that had a full supervision during on the real data. So here we see that say a model for a chair goes from for a sim-trained model with the corrector was about 68 in ADAS score. It goes up to 100, and the ADAS thresholds here were very tight in terms of, I think it was like 2% and 5% of the diameters. We also saw that our method can beat state-of-the-art baselines like DeepGMR and PointNet LK that are trained to do similar tasks of pose estimation. So finally, we also implement the certificate of non-degeneracy, which makes our models strongly certifiable. That is, it not only detects whether input-output is correct or not, but it can also detect whether there is a unique solution for a given partial point cloud. So for example, a partial point cloud of a cap with just a point cloud of part of the head, there are multiple ways you can register a cap. So our model is able to detect that and improve the performance. So just to summarize, what we did was like our aim was to provide sort of a general framework to do for certifiable models for the entire end-to-end pipeline, and we sort of said that the model end-to-end model is trying to solve a problem. It has a solution space X, and a certificate of correctness is something on the input-output pair where the output is mandated to be where this certificate says whether the output produced is in the solution space of correct answers or not, and the non-degeneracy basically said whether the produced output was the unique solution or not, whether the problem had a unique solution or not. So in summary, I would like to say that we can certify end-to-end perception pipelines, and we can use certificates for self-supervised. We can use the certificate input of the outputs produced for self-supervised training, but we only demonstrate it in our work for pose estimation, and this presents an opportunity to explore this and apply this idea to many more tasks in the future. And finally, on some of the cautions or the dirty laundry, so to say. So for certifiable algorithms, many of the solvers we saw are accurate but can be slow, as the polynomial time is different from the real compute time that you put on the hardware. The second things that we saw about robust solvers, while they were robust to very high accuracy, like 90% of outliers, but it can still fail when there aren't many inlier points. For the certifiable models, on the other hand, our goal was to sort of certify and use this method of certifying for self-supervised training, but we have demonstrated only for pose estimation, and there's like a lot of things that needs to be done to extend it to other tasks. And one of the limitations of the model is that the corrector layer, it's a declarative layer and sucks up a bit of compute time during the training. So that's about it. Thank you for listening to our talk. Enjoy the rest of the workshop.